Start? Okay, we are recording, so we're very happy to have Alisha Gupta here today to give an invited talk for the Gregorius Maths Discord server, and she's going to be telling us about supersymmetric quantum mechanics. So Alisha, whenever you're ready, please take it away.
All right, I am going to be talking about supersymmetry today. I'm very excited, so I'm just going to jump right into it. So why are we bothering with supersymmetry in the first place? There's two motivations that are particularly important. The first one is that we enjoy things that simplify systems, right? Like if you have a complex system, you certainly want to study its simple analog in order to deduce some information about the original complex system. And supersymmetry provides a platform to do so. So that's one reason. The other reason is just because there are physical theories in the world that already have supersymmetry encoded in them, and learning supersymmetry would help us learn more, it would help us learn about the behaviors of those physical theories. And we see it's an increasing trend that many physical systems just happen to have this particular symmetry. And so yeah, it's simplification. I'm gonna skip the sketch of the talk. I think you'll just comprehend what the talk is about. Okay. So this is important. This is the big intuition behind all of this. Every time I say something, this is going to be a lot of mathematical formalism to get back at one simple idea. And the simple idea is that supersymmetry can be loosely defined as a correspondence between bosons and fermions. I haven't defined what a boson is or what a fermion is yet, but I will. For now, whenever I say the word supersymmetry, you should always think back to, okay, well, if there exists a fermion, there exists a boson. Supersymmetry, loosely defined, just means a one-to-one correspondence between the number of bosons and, it's a one-to-one correspondence between the bosons and the fermions of a system. Okay, so now it's beneficial if I actually define what a fermion is and what a boson is, but there's really two ways to define the thing, right? There's the more mathematical way, and then there's also the physical way. So the more mathematical way to look at all of this is that a fermion is an anti-commuting object, and a boson is a commuting object. There is a physical intuition behind this, which I will get to, and it's on the slide if you're already reading it, but the intuition you should keep behind what a fermion is and what a boson is that a fermion is an anti-commuting object and a boson is a commuting object. And that should really be the thing in the back of your mind. Okay, but physically, what is it, right? When I say fermion and boson physically, you may think of the pop science babble that is, a fermion is a matter particle and a boson is a force carrier, woohoo. That's not wrong, right? If you have the standard model, you can certainly draw a line, and the particles that carry force will be bosons, and the particles that are matter particles will be fermions. But it's not necessarily a definition. The better definition is that fermions and bosons are the two big classes of indistinguishable particles. All right, great. So what is an indistinguishable particle? An indistinguishable particle, two particles are indistinguishable if particle 1 and particle 2 are indistinguishable if particle 1 in state A and particle 2 in state B is physically equivalent to particle 1 in state B and particle 2 in state A. So the system is equivalent under some exchange of particles. So notationally, I did write that particle 1 in state A corresponds to AB ket. And particle 1 in state B and particle 2 in state A corresponds to BA ket. So I'm going to use AB and BA as basis vectors to construct states. AB and BA are my basis kets, and I'm defining psi of A comma B to it represents a two-particle system where there's some probability associated with beta of finding finding particle 1 in state A and particle 2 in state B and there's some probability associated with alpha of finding particle 1 in state B and particle 2 in state A. So there's just certain probabilities for finding two particles in certain configurations. Okay, so now, presuming that particle 1 and particle 2 are indeed indistinguishable, it shouldn't really matter if particle 1 is in state A or particle 1 is in state B. Like, our system should look equivalent, like it should look physically equivalent. And the way to represent this is if we replace like AB ket with BA ket, everything should be equivalent up to some phase I called here gamma. So again, psi of A comma B equals beta AB ket. Yeah, I trust you know how to read, etc., etc. So beta AB ket plus alpha BA ket equals gamma beta BA ket plus alpha AB ket. This is just a statement that under an exchange of particles, under exchange of particles, you're going to pick up some phase, and that's all. Like, it's going to be equivalent up to some phase. All right, so now I'm just going to like equate the coefficients of AB ket and BA ket. So equating beta with gamma alpha and equating alpha with gamma beta, I get that either gamma equals 1 or gamma equals -1. So either beta equals alpha, right? Either beta equals alpha or beta equals negative alpha. All right, so now we just like are going to plug in. These are our like two scenarios. There's two configurations, and I'm just going to like plug in back here. So if either beta equals alpha or beta equals negative alpha, so if beta equals alpha, then we're going to get alpha AB ket plus alpha BA ket, which corresponds to bosons, right? I just factor out the alpha here. So alpha times AB ket plus beta BA ket. And that's equal to swapping the particles. Like the states are equal. If I have psi of AB and I swap the particles, the state is still equal. All right. So the other case is when gamma equals -1. That happens when beta equals negative alpha. And so again, just plugging in, you're going to get negative alpha AB ket plus alpha BA ket. Factoring out, you're going to get alpha BA minus AB ket. Great. Okay, so now under an exchange of particles, you're going to pick up a negative sign, right? And this is just the statement that fermions are antisymmetric, they're anti-symmetric objects, and bosons are symmetric objects. This kind of corresponds to our mathematical intuition that fermions are anti-commuting things and bosons are commuting things. And so this is kind of just the physical intuition behind it. Fermions and bosons are big two classes of like indistinguishable particles. Questions? Yes? No?
And I don't see any questions in the chat. Someone made a joke about K-Starian addition, but I have not seen any questions. If someone asks the question in text, I'll just read it to you, I guess, because you're probably not looking as well, right? Okay. No, you're doing great. Can I ask one thing? On my end, it's slightly hard since it's zoomed out a little bit on the slides. Can you hit like the Control Plus a little bit so it zooms in just so we can see like just one slide, like in the
Yeah. True.
Oh, good. Okay, that makes it much better. Thank you.
Okay, right. Okay, so a good thing to have, a good thing to construct is something that represents, right? Something that represents the correspondence between bosons and fermions. So you might imagine that a good construction that represents the correspondence between bosons and fermions is something that acts on a bosonic state and gives you a fermionic state, and then something that acts on a fermionic state and gives back a bosonic state. That's exactly like what these Qs are. The Q like operators, they map from the place where the bosons live to the place where the fermions live. Formerly, this is called like the bosonic Hilbert space to the fermionic Hilbert space. Okay, so you should really like think about it like, okay, if I act with Q on any bosonic state, I'm going to get a fermionic state. And if I act with Q on any fermionic state, I'm going to get a bosonic state. These Qs are really like the generator of this specific supersymmetry. They do generate the symmetry, right? They're corresponding fermions with bosons. Okay, good. All right, so now we also have some algebra associated with the Qs. And this is a bit hard to motivate, but this is kind of the intuition you should take. This is kind of the intuition you should take out of it, right? We want that when we multiply any two symmetries together, we get another symmetry generator. So I told you that the Qs were symmetry generators. We want the product of two Qs to be symmetry generators as well. And so we wrote here that Qi squared plus Qi squared equals 2 times the Hamiltonian. The Hamiltonian is also a symmetry generator, specifically like time invariance and time symmetry. But you also want that like Qi times Qj, you want that the Q is anti-commute, right? And the way to kind of explain this is just that like Qi Qj equals 0 because 0 is like the trivial symmetry generator. But honestly, like you should kind of just take it as a postulate and not try to explain it anymore in your head, unless you like go on and try to do field theory or like do Lie algebras. But this is like an important thing that we're going to reference, right? The Qi squared equals the Hamiltonian. If you take nothing else from the side, certainly know that Qi squared equals the Hamiltonian. Okay.
So wait, hold on. Is this like is this a collection of different Qs, or?
Yes. It is a collection of different Qs. So there's loosely like for every fermionic state, there's some Q associated with it. Yeah.
Oh, I see. Okay. All right. Okay.
Okay. So at the beginning of the talk, I kind of said that fermions were anti-commuting objects and bosons were commuting objects. Another way to say commuting objects is the product of anti-commuting objects. So if I multiply an even amount of anti-commuting things, I'm going to get out a commuting thing. And so a good way to discern if our state is bosonic or fermionic, or if it's commuting or anti-commuting, is if our state has an odd amount of anti-commuting things, then in total, in aggregate, it will be a product of an odd amount of anti-commuting things, which is anti-commuting or fermionic. And again, if we multiply an even number of anti-commuting things, in other words, if our state has an even number of anti-commuting objects, then in aggregate, our state will be commuting or bosonic. So when this operator, -1 to the f, it raises -1 to the power f. F is the number of anti-commuting objects in our system. So if f is even, then you're going to multiply an even amount of anti-commuting things, which is commuting. All right, so then -1 to the f. If f is even, then it's 1, right? This is just a statement that if you raise -1 to an even power, then you're going to get 1, and if you raise -1 to an odd power, you're going to get -1. So yeah. In like total and aggregate, you should keep the intuition in the back of your head that the even product of an even amount of anti-commuting things is commuting, and the product of an odd amount of anti-commuting things is anti-commuting or fermionic, bosonic and fermionic. Very good. Let's see. Okay. So, all right, now we kind of want to make, I'm not going to read out the math to you, like, I'm just going to let you, like, read the math for yourself, but I'm going to explain what's on the slide, at the very least. So we want a lower bound for our energy, right? Like, we want to find a lower bound for any, like, supersymmetric system, and the way we do this, essentially, is by claiming that, okay, if we act with h on any psi, we're certainly going to get E times the psi. That's it's a consequence of the Hamiltonian, right? And we said before that Q squared equals the Hamiltonian. So if we want that Q psi times Q psi, which is related to the energy, is greater than 0, if we want the norm squared of Q psi to be greater than 0, then the least E can be is 0. So whenever E is 0, Q psi has to be 0. Unless like psi is 0, unless psi is the 0 vector, then you have a completely like trivial situation. Given psi is not the 0 vector, Q will annihilate any ground state if E is 0. Right? If E is 0, then Q annihilates the ground state. That's like, those are the words you should like take away from the slide if you like don't really understand the math. If in the ground state, if E is 0, Q annihilates psi. Okay, cool. Okay, very good. So, okay. The entire purpose of like this E equal to 0, E greater than 0 discussion, I'll explain. When E is greater than 0, you're going to have two states with the same energy E. You're going to have psi and Q psi. So your boson and your corresponding fermion, or your fermion and your corresponding boson, that have the same exact energy, right? But if E equals 0, you're going to get that Q annihilates whatever psi. Like if psi is the ground state and E equals 0, Q psi is 0. So there doesn't need to exist in the ground state when it equals 0 a Q psi or a corresponding fermion for every boson. And so we get that supersymmetry is kind of broken in the ground state, but it's really just a consequence of how we defined Q squared and H. And it is very important that our ground state specifically equals 0. We don't, like, it could be in some theory that the bosons and fermions equal, the bosons and fermions, like supersymmetry is still preserved in the ground state, but we need that E equals 0 in order for supersymmetry to even exist. And I'll explain that a little bit more. Okay, so this is, again, just a statement. Our logic will break down in the ground state because Q psi is 0. All right, what is the Witten index? The Witten index, as I said, supersymmetry is kind of broken in the ground state because Q acting on psi is 0. There does not exist a fermionic partner for every boson or a bosonic partner for every fermion. So the Witten index is the number of bosonic ground states minus the number of fermionic ground states. This number does not have to be 0. It should be mentioned in excited states, in states with E greater than 0, where E is not the ground state, right? When your state is not in the ground state, your bosons and your fermions have to equal each other. Like the number of bosons has to equal the number of fermions. So the Witten index is kind of trivially 0 whenever E is greater than 0. Okay, so a consequence of this is kind of that we can't have a ground state where E is, like, where you have energy greater than 0. Because then you wouldn't, like, the Witten index would just always trivially be 0 because there would exist a fermionic partner for every bosonic partner, but the way we defined Q, Q has to equal H squared, Q acting on psi must be 0 in the ground state. So it wouldn't really make sense if indeed, like, if E was greater than 0. Like that would destroy our logic that said Q acting on psi must be 0.
So this Witten index is kind of measuring, in some sense, it's kind of measuring how to what extent the statement that, like, for every boson we can also get a fermion fails, right? It kind of measures how much it fails.
It's not that it fails. Okay, so the Witten index is a good way to check if supersymmetry is present. I'll explain that a little bit. In states where E is greater than 0, if our Witten index is not equal to 0, if the number of bosons does not equal the number of fermions, then certainly supersymmetry is broken, right? Like, if it's not the ground, yeah, okay. It's not really a measure of, like, the Witten index, if the Witten index is, like, say, arbitrarily large, it's not really a measure of how much SUSY is broken in the ground state. We kind of, it's not really a measure, no, to answer your question.
Okay.
I don't know, I would have said the opposite. I mean, so, Greg, how did you phrase it? Is the Witten index a measure of how...
Like, how much the statement that like to each boson there we can get a fermion fails.
Fails in the ground state. Yeah, I think it is true if you append the words ground state at the end, right? If you say how much the statement that bosons and fermions are paired fails in the ground state, then what you said is exactly right. That's exactly what the Witten index is measuring, the degree to which that statement fails in the ground state. Yeah.
Okay, I see.
Okay. Well, okay. I'd be kind of careful. Like, I was kind of okay. To like kind of rephrase or summarize, I wouldn't really say it's a measure of how much supersymmetry is broken as like a whole. But certainly, like, yeah, if the question is just that, like, what is the discrepancy between the number of like fermions and bosons in the ground state? Then yes, the Witten index is a good measure of that. But for like a considerable amount of time, that I thought that like the Witten index measured how much SUSY was broken, and that is not the case. Like,
Okay.
right, it's not really a measure of how much SUSY is broken. What's a good measure of how much SUSY is broken is if we have a ground state where E is greater than 0. That is a good measure of how much SUSY is broken. Like, that is spontaneous symmetry breaking. But the Witten index isn't necessarily like breaking of the SUSY as a whole. But yes, in the ground state, that's correct. Good.
I think what happened is that you mapped Greg's question onto a much more sophisticated question about spontaneous symmetry breaking and answered the sophisticated one, but I'm pretty sure he was not thinking about that. So good. Now I think we're on the same page.
Okay, good. Based. Okay, great. This is fun. So superfields are fun things. Superfields are functions of time and objects called Grossman numbers. So superfields, I should say this statement. Superfields are functions of superspace. What is superspace? Superspace has coordinates of time and Grossman numbers. Grossman numbers are anti-commuting objects. I'll explain that more, but I want to give more motivation behind like why we are defining time and these Grossman numbers to live in the space of superspace. Like, how does it relate to what we're trying to represent? Are the symmetry between bosons and fermions? Okay. Well, first of all, it depends on time because quantum mechanics. Quantum mechanics is a quantum field theory in 0 plus 1 dimensions. What does that mean? Well, first of all, 0 plus 1 dimensions just means that there's 0 dimensions in quantum mechanics and only 1 time dimension. It is a quantum field theory means like a completely different thing. What is a quantum field theory is a very good question. It's not a question I'm going to answer. It should be vaguely kind of just thought of as a theory that has quantum things. I'm not... It's a very hard question, and it's particularly undefinable. That's not true, but it's... there's no good definition for it right now, is what I want to say. And I want to put particular emphasis on the fact that quantum mechanics is a theory that depends on time, and that's why we have this like time axis or time dependence in superspace. Okay, so why do we have the Grossman number dependence in superspace? Like, why do you have dependence on the anti-commuting objects? Well, we want to represent a symmetry between fermions and bosons. A way to map between fermions and bosons is by appending anti-commuting things onto commuting things, right? Like if I multiply an anti-commuting thing to a commuting thing, it will become anti-commuting. So this is said differently. If I multiply a boson by an anti-commuting object or a Grossman number, it will become a fermion. If I multiply a fermion by an anti-commuting object, it will become a boson. And so the Grossman numbers, they help us transition from bosons to fermions. Okay, these are the properties essentially of the Grossman numbers. I've told you that they're anti-commuting. Again, they are anti-commuting. A thing that one should emphasize here is that if I multiply 2 of the same Grossman numbers together, so if I take q sub I squared, it must satisfy the property that q sub I squared equals negative q sub I squared. And the only q sub I that can do that is 0. So if I multiply any 2 Grossman numbers together that have the same index, it has to be 0. And that's like a particular point that will come up again. and you'll be kind of confused if you forget it. So q sub I squared equals 0. All right, very good. So, okay, the next point to emphasize is like how the question I posed at the beginning, how does this relate to fermions and bosons? How does it, how does this represent a symmetry between fermions, and how does it represent a symmetry between fermions and bosons? Every single term in this like superfield expansion, this function of time and our Grossman numbers, has to be either commuting or anti-commuting. So if X is commuting or bosonic, then alpha theta 1 has to be commuting. This entire term has to be commuting. Gamma of t theta 2 has to be commuting. This is just a statement that like taking a sum of a commuting thing and an anti-commuting thing doesn't really make a lot of sense. And so we're going to get here, right? If we want to make this term commuting, we want this term to be a product of anti-commuting things. Because if alpha is commuting and we multiply it by the anti-commuting theta, then certainly we're not going to get a commuting object anymore. So if x of t is commuting, then alpha of t must be anti-commuting. Gamma of t must be anti-commuting. Beta of t must be commuting, because we want to preserve theta 1, theta 2 is commuting, and we want this entire term to be commuting. So you can quickly see that if this pattern continues, we're going to get a correspondence between fermions and bosons in this way through the component fields. So the things attached to the thetas, they're called component fields. X, alpha, gamma, beta, nu, omega, they're all component fields. So these component fields, they describe the correspondence between fermions and bosons. So for each boson X, there exists a fermion alpha. The commuting, anti-commuting. Very good, very good, very good. Okay, this is just written more explicitly. It's given in like an example format, but if I have a superfield that depends on time, theta 1 and theta 2, and I expand it out and I get x of t, gamma, theta 1, alpha of t, theta 2, etc., etc. If x of t is bosonic, gamma of t and alpha of t must be fermionic, because theta 1 and theta 2 are anti-commuting, and we want all of our terms in our expansion to be commuting. So again, the correct intuition to take away from these superfields is that the component fields, these x, gamma, the alpha, and the beta, represent the one-to-one correspondence between the bosons and the fermions. Okay, we're going to go through a very fun derivation of q sub I now. In superspace, so when I say q sub I in superspace, I really mean how does q explicitly look in terms of like my superspace variables. So these the t and the theta 1, the theta 2, the theta n. So there's two particular motivations behind Q, right? Like we have one that Q sub I squared has to equal the Hamiltonian, and we have the second motivation that Q maps from fermions to bosons. So keeping both of those intuitions or motivations in mind, we logically kind of try to think of objects that first map between fermions and bosons. So, as I said before, theta and d by d theta are good are good guesses for this. I'll explain why. Right? Theta is an anti-commuting object. If I multiply an anti-commuting object with an anti-commuting object, I'm going to get a commuting object, right? If I go, this is just going from a fermion to a boson. If I have d by d theta, that's eliminating an anti-commuting object from an anti-commuting object, which will give me back a commuting object. This is like reiterating the same fact over and over again, just to like really drill it in. But these are the two guesses we could have for Q sub I if we want Q sub I to map from fermions to bosons. It could either be theta I plus some terms or d by d theta I plus some terms. And it should be noted that the terms should maybe also map from maybe should also map from fermions to bosons. So the terms should certainly have some theta I or d by d theta I dependence. I'm just going through like one part of the argument at a time. So we're working in units where h bar equals c equals 1. So taking h bar to be 1, we get the dimensions of h bar to be 0, and now we're just going to do dimensional analysis with our two guesses. So we know that q sub I squared equals the Hamiltonian. This means the dimensions of q sub I squared has to equal the dimensions of the Hamiltonian. And we said before, I believe I said before, right, I did, that the Hamiltonian is equal to IH bar d by dt. Again, we're working in dimensions where h bar equals 1 equals c. So time has length dimensions at this point. And therefore d by dt has dimensions of -1. So we want the dimensions of q sub I squared to equal -1. This is just the same in that we want the dimensions of q sub I plus q sub I to equal -1. And therefore the dimensions of q sub I has to equal -1/2. All right, so now we're going to check our two guesses and see which one fits this constraint. We want each term in our guess, right, to have dimensions of -1/2. A for now kind of unmotivated fact about the thetas is, you can kind of make it motivated through another way, but a for now unmotivated fact about our thetas is that theta sub I has dimensions of 1/2. And so d by d theta I has dimensions of -1/2. And so the logical thing to do is to pick q sub I equals d by d theta I plus terms if we want the dimensions of q sub I to equal -1/2. Okay, now here's how we get the rest of the terms. We make the argument that if we want the anti-commutator of q sub I and q sub I to equal I d by dt, we certainly want q sub I to have some dependence of d by dt. And so we kind of make this arbitrary guess for terms that it should at least contain a d by dt plus some other thing to make all the dimensions work out, which I've called c here. All right, so now we go back to our old buddy dimensional analysis, and we want the dimensions of q sub I, again, to equal -1/2, which means the dimensions of c plus the dimensions of d by dt, which is -1, should equal -1/2. So the dimensions of c is 1/2. And again, okay, the logical thing to do is to say, okay, c equals theta 1. Or theta I apologize. All right, so now here's our guess so far. We have q sub I equals d by d theta I plus some constant a times theta I times d by dt. Now we're going to go through a kind of messy procedure to obtain the constant I.
Sorry, before the messy procedure, can I read? There was a question in the chat which I should probably read before getting into the details. So K-Star was asking, can you explain why it is that a product of anti-commuting objects, like a theta 1, theta 2, he said it's not clear to him why that product is commuting. So why is it that if you have a theta 1, theta 2, and a theta 3 for theta 4, those products, why do those things commute?
Okay, so I had the same question a long time ago. Yeah, I had the same question a long time ago, and so I did it on an overleaf, and I can show you that right now, and I think it would clear up a lot of things for everyone else too. It's a very silly calculation, but it does make sense once you do it out. I particularly had this because I knew it would be a particularly resourceful thing. Right, okay, so good. Here, I'll walk you through it if you'd like, but this is the proof of it done. Yeah. So we want that. I've chosen theta I, theta j, theta 1, theta 2 to just be members of the collection of objects that are anti-commuting. So then theta I, theta j has to equal negative theta j, theta I. Theta 1, theta 2 has to equal negative theta 2, theta 1. And again, just every permutation has to equal the negative of the objects flipped. Okay. So now we calculate theta I, theta j, or the commutator of theta I, theta j, theta 1, theta 2, and we sure hope that this is 0, right? Okay, so then we go through theta I, theta j, theta 1, theta 2, minus theta 1, theta 2, theta I, theta j. All right, this is just, we're going to be pulling out like a lot of negatives, but you get theta I, theta j, theta 1, theta 2 equals, oh, that's funny. There should be a negative sign here, but it goes away here, so it doesn't really matter. You're just like going to keep pulling out negatives, keep pulling out a negative, keep pulling out a negative, and eventually you get theta I, theta j, theta 1, theta 2 equals theta 1, theta 2, theta I, theta j. So now you can indeed see that theta 1, theta 2, theta I, theta j minus theta 1, theta 2, theta I, theta j equals 0. Good?
Yeah, I think that's the answer. I mean, the short version is indeed like if you have theta, 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 and you want to move everything past the other, then you just push this theta past the two thetas, so you get 2 minus signs. Then you push the other theta again past 2 thetas, so you get 2 minus signs. Overall 4 minus signs, which is 1, and then you flip the order. So if you have an even number of them, you push back and get an even number of minus signs. So that's the answer.
True. Okay, now it's time for messy calculations. It's more beneficial if you just kind of like read it, but I will like guide you through it to some extent. It's not like a hard calculation, and you could probably just think about it a little bit in your head and understand why A has to equal I. But really just, I'm implementing the fact that Q sub I, the commutator of Q sub I with Q sub I has to equal 2 times the Hamiltonian. And again, we're taking the Hamiltonian to be I d by dt because h bar equals 1. So the anti-commutator of d by d theta with d by d theta has to equal 0. Here I'm taking out A on the left and d by dt on the right, and this is just going to turn it into the anti-commutator of theta sub I with theta sub I, which is 0. So you're really only left with like these two terms, and then you expand it out and you get nonsense, right? You get this, which indeed does equal 2I d by dt. Okay, so then you're just going, oh, this should be an A. C equals A, I'm sorry. But anyway, you factor out an A on the left from this entire expression and a d by dt on the right. And this gives you the this gives you the anti-commutator of d by d theta I with theta I and theta I with d by d theta I, which in our original postulate, like when I told you what Grossman numbers were, I did indeed say that this anti-commutator was 1 and this anti-commutator was also 1. So you do get 2a d by dt equals 2I d by dt, and a equals I. Okay, that's enough messy calculation. Yay, so we have one singular slide that tells us what Q sub I is. After all that dimensional analysis, all that equation stuff, this is Q sub I in superspace. This is Q sub I calculated via like the superspace coordinates time and theta 1 through theta n. Good, very good. Okay, good. So this is an exciting tidbit. The superspace Lagrangian. What is the superspace Lagrangian? These are going to be 3 steps to obtain a physical Lagrangian that has supersymmetric properties encoded within it. What does that mean? Great question. So, I'm sorry, how are we going to do that? That's actually the better question to ask. We're going to do that by first constructing like some function of the superfield, some function of a thing that already represents supersymmetry, that is dependent, like this function of the superfield is dependent on kind of the theory you're working with. Like there's no one uniform way to take a function of the superfield. It just depends on what like properties of the theory you're studying are. Okay, so now the honest to God like physical Lagrangian of your system will be the last component of this function, of this original function of the superfield. It will be the last component. of that expansion of that function. And there's a particular reason for this, and we're going to go into this gigantic digression into like why it is that the last component of A is the physical Lagrangian. I'll explain that, but for now, just keep it in the back of your head. Okay, then the third step is to go through a procedure to actually obtain the last component of A. This is called Grassmann integration. Towards the end of the talk, we'll talk about it. Okay, I didn't read this part up here, and I should probably explain what it means. So, why are we even doing this? Like, why do we care about the Lagrangian? It kind of just seems like I placed it in front of you. So, the Lagrangian is like a very, very good way to represent a quantum field theory. I struggled a bit in like the beginning trying to explain what a quantum field theory was, but there are things we study, and they're very complicated things in particular, and we're interested in simple cases of quantum field theories. And simple cases are ones that can be represented via a Lagrangian. A Lagrangian is just like some quantity that encodes like properties of the energy, but so that's essentially like why we want a Lagrangian, because a Lagrangian can describe our QFT whilst also like describing some properties of supersymmetry. And as we said, if we implement supersymmetry on a particularly complicated QFT, then you would get a simple QFT in response. Okay, great. So now we should like elaborate on this point. We should elaborate on why the last component of A is the physical Lagrangian, and A is just some function of X. So let's go on. Okay. So we say that Q is the generator of symmetries. The generator of symmetries, as I said before, like Q represents the symmetry between bosons and fermions very directly, right? And so we want Q acting on any like action to be 0, and we want like this is particularly because we want e to the q to leave any action s alone. So this is like the kind of motivation for what a good Lagrangian would be. A good Lagrangian would be a Lagrangian such that s of the Lagrangian, q of s of the Lagrangian, where the s is equal to the action of the Lagrangian, is 0. So Q acting on the action of the Lagrangian is 0. We want a Lagrangian that satisfies that particular property. And so let's like dig deeper. As I said before, the S is just equal to the integral of the Lagrangian over all of time. So, okay. We're acting with Q on this thing, and as I said before, we want Q acting on S to be 0, because we want Q to be a generator of symmetries, and we want e to the q to leave anything we act on, any S we act on alone. Okay, so I just like I push the Q into the integral, and I obtained some function df by dt. Okay. Making the assumption that like f dies in like the far and past future, we get when Q acting on the Lagrangian is a total time derivative, Q acting on the action is 0. So we want Q acting on the Lagrangian to be a total time derivative in order for Q acting on the action of the Lagrangian to be 0. And that's particularly important because we want Q to be a generator of symmetries. So we want, again, Q acting on L to be d by dt of something. Okay. The correct question to ask after I've placed this equation in front of you, that Q acting on L should be the total time derivative of something, is what Q? Like, what Q are we talking about? Are we talking about the Q we explicitly calculated in superspace out of time theta 1, theta 2, theta n? Or are we talking about the Q that maps from fermions to bosons directly, that lives in like the Hilbert space? That's very abstract. That's a good question to ask, and it's particularly important. And the best way to see the difference between these Qs, like the Q of superspace and the Q ordinary, is just to like do an example and explain what I mean. All right, good. So back to like what Greg asked in the beginning. Indeed, like Q sub I, there is there are many different supercharges. So right here we're acting with Q sub 1. We could also have acted like Q sub 2. There exists many supercharges. Okay, so acting with Q sub 1 on the superfield, you're going to obtain, just like doing it out, d by d theta on x is nothing, d by d theta 1 on the second term is kappa, or negative kappa in particular, because you have to move the theta 1 past the kappa, and they're both anti-commuting. This is 0, and this is, again, moving this psi past the theta 2, you're going to get negative psi of t theta 2. Okay, then second term, keep going. Okay, you're going to obtain this, is the point, when you do Q1 acting on the superfield of x. X of t theta 1 theta 2. Okay, so the way to think about this ordinary Q that maps from fermions to bosons is it's a correspondence between the terms that have the same amount of thetas in our original superfield with the terms that have the same amount of thetas in the action of Q on that superfield. So, for example, X and kappa both have no theta dependence. So X and kappa Q acting on X, Q ordinary acting on X gives you kappa. The way we write the action of the ordinary Q on any bosonic function is via a commutator. This is like, I could also like show you why this is true, but I mean, I guess you could just take it that it is true. The way you act, the way you act with Q on any like fermionic function is via an anti-commutator. So this just means, okay, I'm going to act with my operator Q on a fermionic function, and I'm going to get out I x dot. Why is this? This is because kappa of t theta 1 has a theta 1 dependence, and I x dot has also a theta 1 dependence. All ordinary Q is doing is corresponding terms with the same theta dependence in x of t, right? X of t theta 1 theta 2, and the action of Q on that superfield. So terms with the same amount of thetas, or not the same amount, the same thetas get corresponded together under the action of the ordinary Q. I didn't write it here, but like, for example, commutator of Q and psi will be, negative I gamma dot. Okay, so how does this like correspond with fermions to boson mapping between fermions and bosons? Great question. Q acting on an X, which is a boson, gives you back a fermion. Kappa is a fermion. X is a boson. Again, here we have Q acting on a fermion. You're going to get back a boson. So this is the entire point, right? Like we're acting with our Q, which we know will take away our theta 1 or our thetas, or it will add thetas back, right? It'll transition from fermion to boson, and then we're saying, okay, we're going to make that point even clearer via this like ordinary Q, which really like exemplifies you take a boson and then you get back a fermion. That's all it's saying for now. Okay. So again, after going through that entire digression of like Q ordinary versus Q Suzy, this original statement really becomes the ordinary Q acting on L gives you a time derivative. Okay, so why does the top term, like why does the last component of our superspace function, or our function of our superfield A, satisfy that property? Why does Q ordinary acting on that specific function give you d by dt? If you act with the top component of A is your maximal monomial term. This just means that it will have the maximal amount of thetas. It will be the term that has the max amount of thetas. It has theta 1 up to theta n. And this will get corresponded with something, right? Something underneath the action of Q Suzy, the supersymmetric Q on X. that also has theta 1 up to theta n. But the only way to receive a theta 1 under the action of Q supersymmetric, like Q built in the superspace, is via our term theta 1 d by dt. And so either Q acting on a certain term will destroy that term. Either Q acting on that term will give you nothing, or it will give you theta d by dt. Okay. And so if Q ordinary is really corresponding terms that have the same amount of theta dependence, then the only way to receive a theta under like Q SUSY is via that theta I d by dt term. And that's why Q ordinary satisfies, that's why the top component of A satisfies the property that Q ordinary acting on it will give you the total time derivative, because the only way to obtain a theta I under like the SUSY Q we built in superspace is via this d by dt theta I term we had. Yes? Good? Questions?
There were some comments in the chat which I told people to ask at the end, but otherwise it seems like everyone's happy.
Very good. Okay, so I believe I've kind of convinced you, hopefully, that the last component of A is certainly your physical Lagrangian. I told you that there's a procedure to obtain that physical Lagrangian, and that's what we're going to talk about here. So the way to obtain that physical Lagrangian is via a procedure called Crossman integration. So I'm just going to explain it right now. It's very much like a mathematical formalism, and you should kind of think about it that way. So I'll explain it very quickly. So taking the integral of theta I with respect to theta I will give you 1, and taking the integral of theta I with respect to any other theta will give you 0. This means that if I take the integral of if I take the integral of A of t, comma, theta 1 through theta n with respect to d of theta 1 through theta n, the only term that will survive is the term that has all of the thetas, right? Because anything else would just equal 0. And the term that has all the thetas is our top term. It's our last term. It's d of t. And so this is just like a fancy procedure, essentially, to obtain our top term, our last term, d of t. Okay, so that's Grossman integration. Now we turn to a very fun closing example by our good friend Clay Cordova. Great guy. He euthanizes people. Okay. This is kind of like crap I could explain, but I want to emphasize a particular point, and I think it's like, it's a good point. Like, it's a good example to see and think about. I could explain this crap, actually, but it's not really crap. It's interesting. But whatever. So for now, this is our superfield. This is its definition. This is what Mr. Cordova chose. And so, okay, D can just think about it for now as, well, actually, I'll explain it. Why not? D is the covariant derivative. So what is the covariant derivative? Mathematicians, please don't bite me, but if you take d by d theta on any object, you're going to get somewhat of the correct answer, but you're also going to get some like other crap, because you have things that don't necessarily commute, and you're going to get the answer plus some crap. And so what the covariant derivative kind of does is it deletes that crap. So this is just saying, this is the crap I obtain by acting with d by d theta normally, so I'm just going to delete it. Okay, so I'm acting with d on my superfield X, and this is what I obtain. That's all it's saying for now. So, okay, here's a particular point to emphasize. This plus this is A. That is my superspace Lagrangian. It is literally just some function of my superfield. It is just some function of my superfield. It's some function of my superfield plus another some function of my superfield. And all that's happening right now, all of this is literally just him doing Grossman integration and extracting out the last term. and he's extracted it out. This is the last term. This is the top term of A. A is equal to W of x t theta bar plus dx star plus this is A. And then you're literally just taking the Grossman. You're literally just Grossman integrating it, and you're obtaining the last term. And then you actually have like a successful SUSY Lagrangian. And that is the entire point. Like this is the entire point. And it's like it's not as hard as it looks, or it's not as like it looks particularly like intimidating. But that is like the entire summary of everything I've explained so far. It's literally just taking some function of x. Oh, here we go. It's taking some function of x, and then integrating it with respect to all the thetas and obtaining the top term, because the top term has some great properties. And that's kind of the summary of it all. Yeah. I hope you enjoyed that talk. That's all I have for you today.
Good. All right. I don't have the applause button on Zoom. I usually applaud at the end of talks, but I guess I'll do manual applause or something like that. Good. Okay. Let's thank Alisha for the very nice talk. And I guess it is time to open to questions. Greg, did you have something?
Yes, I'll turn on my camera so you can see that I'm smirking while asking this.
Mocking?
No, he said smirking, not mocking. He's just British, smirking.
Smirking. I was trying to imitate the smirk. Oh, God. Okay, continue.
I couldn't help but note that qi squared equals 0 somewhat resembles a chain complex. And so is there a cohomological interpretation of this whole kind of construction that we've...
Q sub I squared not equal to 0. Q sub I squared equal to the Hamiltonian.
After you rotate, though, he's thinking of the complex Q's. So the real Q's, Qi squared to H, the complex one squared to 0. Yeah, that's after Clay rotates to the Q and Q bar, then it's correct.
Right. Okay, funny. Yes, that's true.
Yeah.
Great question, Greg.
Great question. If you scroll to the next section in the notes, he will answer. Clay answers
this question. He will answer your question. What is cohomology, Greg? What is cohomology? Let me tell you what it is. It's sticking tape from this end of the car to that end of the car, and this end of the car to that end of the car, and this end of the car to that end of the car, and then that's cohomology.
I don't know what that means.
I don't know how to respond to that.
Thank you. Oh, wait, the person who would get that reference isn't even here. That's so funny.
Oh, you assumed Brendan was going to be here for the talk? You assumed he would be a good friend and listen to your talk?
Really? That's so confusing.
He did not come. Your assumption was false. He was not a good friend.
That's confusing. It's really confusing, actually. Interesting.
He's probably sleeping.
Yeah, he seems to sleep quite a lot, but
you guys are terrible. Yeah. Somebody should euthanize him or something.
He's hibernating and thinking about tropical geometry.
Tropical geometry is so interesting. I had it. Oh my god. I had a whole thing yesterday with my friend David, who's also Tetra's PhD student, about tropical geometry yesterday. We went like fucking bananas. It was great.
That's very good. But we should probably address the original question. So in complex coordinates, when the Q squared is 0, indeed, there is a cohomological interpretation, which Clay explains in the next section of the notes. And the way to think about it is if the coordinates x, not the capital X, the lowercase x, in Alisha's superfield, are coordinates on a manifold. So you think of your quantum mechanical theory as describing a particle moving on some manifold, and the coordinates on that manifold are the xi, then indeed Q squared will be 0, and you can show that Q corresponds to the D, the exterior derivative, in the de Rham cohomology of the target space manifold. So there's a very beautiful interpretation where the SUSY Q corresponds to the target space D, the de Rham cohomology, and the Witten index, which Alisha showed us, which is an invariant of the quantum mechanical theory, the Witten index turns into the Euler characteristic of the target space manifold. So it's an alternating sum of Betti numbers. It's the cohomology, the dimensions of the cohomologies with -1 to the p. So there's a very deep connection between this entire story that Alisha just told us and cohomology, which would probably take at least another full talk to explain. But it's very nice. Yeah.
Anything else? Questions?
Yeah, there's a lot of people here. Other questions?
I just wanted to get that off my chest.
Wow, that's all great. Good. Let's see if there were other talks or other questions in the chat. K-Star was going to complain about Grossman integration, but then he immediately left right before you introduced the Grossman integration. So I thought there was going to be a question about that, but then there wasn't one, unfortunately.
No.
Yeah.
You should invite Clay. Well, let's ask Tetra what he's doing, actually. Oh, everyone can see my screen. That's true.
Yes. Is he even online? He is not online.
I don't have a phone. I could obtain a phone and ask where that person is, but
He's
so funny. No, it's confusing. It's weird confusing.
It's unfortunate because he did say he was excited. He said earlier in a group chat that he was excited for the 2 talks this weekend, neither of which he came to, and one of which was his talk.
I should have invited David. That would have been an intelligent thing to do.
Yeah, no, that would have been nice. Yeah. Let's see. What are good questions to ask? You explained the thing about products of anti-commuting quantities being commuting very nicely, which is good. Another thing someone might have asked but did not ask is, why is it that a general function of the thetas, so you introduced a superfield as a function of t and the thetas, and then immediately wrote it as some expansion. So it's a component plus a theta times another component plus theta times another component with finitely many components or something like that. Mm-hmm. So the question someone might have asked is, why is it the case that a general function of thetas has to have one of these finite expansions in component fields, right? You would never say that about a function of ordinary coordinates. A function of t, you would never say is determined by finitely many components or something. So someone could have asked, why is that true for thetas?
Something like that. But wouldn't the answer just be, okay, it doesn't really make any physical sense for okay, what does the n correspond to? What is the theta 1 through theta n corresponds to? It corresponds to the number of q's, right? If I have theta 1 through theta n thetas, then I certainly have q1 through qn supercharges. And it only makes sense for us to have a finite amount of those. I think you said this at one point, but sorry, I think you said the following reason at one point, which I'm about to say. You said something analogous to, okay, you can only have 13 supercharges in any quantum field theory, because if you don't, then the entire thing breaks down. And so my reasoning, if anyone asks that question, would be, okay, it doesn't really make sense for us to have an infinite amount of supercharges, and that's really the reason why the theta expansion would end.
Oh yeah, well, okay. There's 2 questions. So you've answered a more difficult question than the one I was thinking of. The more difficult question is, why would we only have finitely many thetas in a theory? Period. That's difficult to answer because indeed you have to invoke this Weinberg-Witten theorem, which you probably don't want to explain. The easier question would be, fix the number of thetas. Suppose there's 2. So we've agreed ahead of time there's 2 thetas. So why is it that a function of 2 thetas should have a finite series expansion where it's the function x of theta 1, theta 2 has a lowest component with no thetas, and then a theta component, and a theta component, or a theta 1 component, a theta 2 component, and a theta 1, theta 2 component? Why is it that an arbitrary function of 2 thetas has this finite Taylor series expansion? Ordinarily, a Taylor series expansion would have infinitely many terms. But here you've written a function of the thetas, and it only has 4 terms, right? It has lowest component, theta 1 component.
Wouldn't all of them, wouldn't any other permutation of thetas just disappear?
Yeah, that's the answer. Yeah, because you would have, in general, you would have an infinite Taylor series with arbitrarily many terms, but because the theta squared is 0, all of the terms are going to be 0 past the top term, right? That's something someone could have asked but did not ask. But
Tetra should have asked it.
He probably would have made some more frustrating comment about Grossman integration or something.
So true, Queen.
Yes, Queen.
Slay. Slay.
Let's
What do you do? What do you do, Greg?
What do I do?
What do you do all day?
I don't know. That's a good question. I just kind of waste my time basically in different ways.
He plays chess.
He does what?
Did he say plays chess? What did he say?
Yeah, that would be accurate. I mean, I spent like all morning playing chess this morning, and then I went out, and then I spent a few more hours playing chess, and then I attended this talk. That's about it.
Oh, based. That's very good. How's Britain?
I don't know. It's British.
It's like asking a fish, "How is the water?"
Look, K-Star joined. He can answer. How is Britain? K-Star.
K-Star is British?
Yes.
Yeah.
British?
British.
Let's just ask Tetra who that person is. Tetra. Oh, wait, hold on. I have no clue what I texted Tetra last, actually. One should not do that.
He was awake earlier as of 2 hours before the talk. He posted
Yeah, he
something.
probably just, forgot or something.
Yeah, despite the fact that we pinged twice or something, but interesting. Yes.
Starting college essays, he's got to get into MIT. Something like that.
I saw his drafts. They look fine. I don't know if he has to rewrite all of them or something like that.
He's so, devoted. He's, devoted to such a gigantic extent. I'm applying, and that's crazy. I should be doing that because I would probably need to do that in order to even succeed at what I'm doing. But him doing it, he's Brendan Halstead. It's not difficult. You just do it. You're a senior. You just apply.
Yeah, he's an excessive human. He likes to spend excessive amounts of time
following the rules.
Yes, spending 200 hours on the problem set for the Friends application.
Stop. That was so bad. That was such a thing to do. I'm not doing that. If I apply to that place, I will not be doing that.
Yes, that is rather an inane amount of time, I would think. But he seemed to enjoy it.
Yeah, he did indeed.
I don't think I could. I don't think I could spend 200 hours on anything. To be honest, I would give up.
Yeah, something like that. It's it's either you give up, or you get there comes a point. It's not even a vaguely interesting thing. You just whatever. I'm doing a thing where it's I'm bitching. I should stop. But he's funny. I like him. He's good. Fond.
Bitching is good. Maybe I should stop the recording if we're going to start bitching. But before I stop the recording, are there any other questions about the supersymmetry and or physics content that we want to get on the recording from anyone?
Evidently not.
No question. Okay, I will stop.